What if everything you've ever known, every star, every galaxy, even the fabric of reality itself, is just one page in an endless cosmic book? Picture this: our universe, vast and mysterious, might be nothing more than a single layer in an infinite stack of realities, each one vibrating, shifting, and existing just beyond our grasp. This isn't science fiction, it's the mind-bending essence of brane theory, a revolutionary idea in theoretical physics that suggests our reality could be one of many membranes, or branes, floating in a higher dimensional space. Think of it like a cosmic lasagna, with each layer representing a separate universe, each with its own laws, its own history, and maybe even its own version of you. The implications are staggering. If brane theory holds true, it would rewrite everything we thought we knew about existence. Suddenly, the Big Bang isn't just the birth of our universe. It could be the collision of two branes, a violent meeting of realities that set everything into motion. Dark energy, that mysterious force pushing our universe apart, it might be the gravitational pull of a neighboring brane, tugging at us from just beyond the edge of perception. And what about those strange voids in space where matter seems to vanish? Could they be portals, thin spots where one universe brushes against another? The questions pile up, each one more thrilling than the last. But here's the real kicker: if branes exist, then every possible version of reality you can imagine, and countless more you can't, might be out there, separated by nothing more than a dimension we can't see or touch. It's a concept that stretches the limits of human understanding, yet it's rooted in cutting-edge science, not fantasy. Over the next few minutes, we're going to peel back the layers of this extraordinary idea, exploring how brane theory could answer some of the universe's biggest mysteries, and why it might be the key to unlocking the next great leap in physics. Buckle up, this is going to be a journey unlike any other. At its core, brane theory challenges the way we picture reality itself. Instead of imagining our universe as an isolated bubble floating in nothingness, think of it more like a sheet of paper, thin, flat, and just one of countless others stacked together in a vast, unseen dimension. These sheets, or branes, aren't just abstract ideas. They're dynamic, vibrating surfaces where entire universes could exist, each with its own physics, its own stars, and maybe even its own life. Now here's where it gets wild. Our familiar three-dimensional world, length, width, height, might just be a tiny slice of something much bigger. According to string theory, the universe could actually be floating in a space with 10 or even 11 dimensions. We can't perceive these extra dimensions because they're curled up incredibly small, or because we're stuck on our own brane like ants crawling across a single page in a book. But gravity, the force that holds galaxies together, might be the one thing that doesn't stay put. It could leak between branes, which would explain why gravity feels so weak compared to other forces. Imagine shouting into a wall, some sound gets through, but it's muffled. That's how gravity might behave, seeping faintly from one reality into another. To wrap your head around this, picture a skyscraper. Each floor is its own brane, its own universe, with people living their lives completely unaware of the floors above and below. Now imagine if a light could shine through the entire building, flickering faintly between floors. That flicker could be gravity, the only hint that there's anything beyond the walls of your own reality. It's a staggering idea that we might be living in a cosmic high-rise with entire worlds stacked above and below us, forever just out of reach. And if that's true, it raises even deeper questions. Could there have been moments when these branes touched, sending shockwaves through reality? Some scientists believe the Big Bang itself might have been a collision, two universes smashing together like cymbals in a silent symphony, unleashing energy that birthed everything we know. Or what about the mysterious dark energy accelerating the expansion of our universe? Could it be the gravitational tug of a nearby brane, stretching space itself as it drifts away? The possibilities are as thrilling as they are endless, painting a picture of reality far stranger and far more interconnected than we ever imagined. The connection between brane theory and string theory isn't just a loose analogy. It's the very foundation that makes the idea of multiple universes mathematically possible. String theory, the framework that suggests all particles are tiny, vibrating strings, also predicts the existence of branes as natural extensions of its equations. Think of it like this: if string theory is the blueprint for reality, then branes are the floors of the cosmic skyscraper it builds. They aren't an afterthought, they're baked into the math from the very beginning. This idea took a huge leap forward thanks to physicists like Randall and Raman Sundrum, who showed how extra dimensions could be warped in ways that make branes not just possible but inevitable. Their groundbreaking work revealed that gravity could be trapped on one brane, like ours, while other forces, like electromagnetism, stay confined to their own layers. Picture a river flowing down a mountainside. Gravity might be the water carving deep channels, while other forces trickle along shallow grooves. This warping explains why gravity feels so weak in our universe. It's spilling into dimensions we can't see, diluted by the vastness of higher dimensional space. What's fascinating is how these theories solve puzzles that have stumped scientists for decades. Take the hierarchy problem, for instance. Why is gravity billions of times weaker than the other fundamental forces? In the Randall-Sundrum model, the answer lies in the geometry of extra dimensions. Imagine two rooms separated by a long hallway. If you shout from one room, your voice grows faint by the time it reaches the other. Gravity could work the same way, its strength fading as it crosses the gap between branes, but the implications go even deeper. If branes exist, they might not just be static sheets floating in space. They could be dynamic, rippling surfaces. Collisions between them could trigger cosmic catastrophes like the Big Bang, or even create cyclical universes that birth, expand, and collide anew in an endless cosmic dance. Some theories suggest that the strange patterns in the cosmic microwave background, the afterglow of the Big Bang, might bear the scars of these ancient brane collisions, like fingerprints left by realities we can no longer see. The beauty of this idea is how it ties together the biggest mysteries in physics. Dark matter could be particles from a neighboring brane, barely interacting with ours except through gravity. The accelerating expansion of the universe, maybe it's the pull of another brane drifting away, stretching space-time like taffy. Even the elusive theory of everything, the dream of unifying quantum mechanics and general relativity, might hinge on understanding how branes interact in higher dimensions. For centuries, we've imagined the universe as a solitary stage, with galaxies, stars, and planets as its only players. But brane theory, rooted in the elegance of string theory, paints a far grander picture. One of countless stages, layered and invisible, each hosting its own version of reality. And the most exciting part, we might be on the verge of detecting them. Experiments with particle colliders or studies of gravitational waves could one day reveal the faint echoes of these hidden dimensions, proving that our universe is just one page in an infinite cosmic storybook. While brane theory paints a vivid picture of stacked realities, it's not the only idea suggesting we live in a multiverse. Quantum mechanics offers the many worlds interpretation, where every decision branches reality into infinite parallel timelines, like a tree splitting endlessly at every fork. But here's the key difference. In many worlds, these universes exist as probabilities, ghostly echoes of what could be, while branes are tangible, physical layers, each with its own concrete existence. It's the difference between a hall of mirrors and a library, where every book is a separate, solid universe pressed against others in higher dimensional space. Then there's the inflationary multiverse, where cosmic inflation spawns bubble universes like froth in an endless ocean. These bubbles float apart, each with its own unique physics, but they don't interact, they're isolated islands in a vast sea. Brane theory flips this idea on its head. Instead of drifting bubbles, imagine a ream of paper where universes are fixed in place yet potentially close enough to touch. A collision between branes isn't just possible, it might be what sparked our own Big Bang. What sets branes apart is their geometric elegance. Other multiverse theories rely on abstract probabilities or chaotic expansion, but branes offer something far more structured, a cosmic architecture where universes are literally layered like floors in a building. Gravity could seep between them, dark energy might be their gravitational shadow, and even the voids in our universe could be places where two branes nearly meet. It's a framework that transforms the multiverse from a hazy concept into something almost tactile, a stack of realities we might one day detect through the faintest tremors in space-time. The real magic lies in how Brane theory bridges the gap between the fantastical and the testable. While other multiverse ideas remain speculative, branes emerge naturally from string theory's math, offering clues we could actually pursue. If future experiments find traces of higher dimensions or anomalies in gravitational waves, we might not just prove the multiverse exists, we could finally map its structure, revealing our place in a cosmic stack of realities. The Ekpyrotic universe model turns the traditional Big Bang story on its head. What if our universe wasn't born from a single explosive moment, but from a cosmic fender bender between two parallel realities? Picture this: two branes drifting through higher dimensional space like sheets of paper suspended in a breeze, slowly drawn together until bang, they collide. The energy of that impact could have ignited the fireball of our universe, scattering matter and energy in a searing flash we now call the Big Bang. But here's what makes this idea revolutionary. Unlike classic inflation theory, which relies on a mysterious force stretching space faster than light, the Ekpyrotic model explains the universe's smoothness and flatness through something far more tangible: the gentle, gradual approach of two branes before their fateful crash. Think of it like kneading dough. If you stretch a lump unevenly, it develops wrinkles and tears. But if you press it slowly, evenly from all sides, it flattens and smooths out. That's what might have happened as those branes inched closer over eons, their gravitational pull acting like cosmic hands, ironing out any irregularities long before the collision. This could explain why our universe looks so uniform in every direction, with no jagged edges or chaotic hotspots. No need for inflation's abrupt stretching, just the natural smoothing of two massive surfaces preparing to meet. And the surprises don't stop there. The Ekpyrotic model also tackles one of cosmology's biggest headaches, the flatness problem. Our universe's spacetime is eerily flat, like a perfectly balanced sheet, with just enough matter and energy to avoid collapsing or tearing apart. Inflation theory says this happened because space expanded so fast it flattened out, like blowing up a balloon to enormous size. But the brane collision idea offers a sleeker solution. When those branes smashed together, the energy released wouldn't just create a hot, dense universe, it would also set the stage for that perfect flatness, like two panes of glass shattering into flawlessly even fragments. What's truly mind-blowing is the cyclical nature of this idea. If branes can collide once, they can collide again, meaning our universe might be stuck in an endless loop of creation and destruction. Imagine two sheets drifting apart after the crash, eventually drawn back together by hidden forces, only to collide anew and birth another universe. It's a cosmic heartbeat pulsing across dimensions, with each beat writing a fresh chapter in the story of reality. Some theories even suggest the dark energy accelerating our universe's expansion could be the tug of an adjacent brane pulling us toward the next collision. The implications are profound. If the Ekpyrotic model is right, the Big Bang wasn't a one-time event, it was just the latest in an infinite series of cosmic rebirths, each collision erasing the past and starting anew. And while we can't yet peer beyond that initial moment, future experiments might find clues in the faint ripples of gravitational waves or the subtle patterns of the cosmic microwave background. These could be echoes of the brain that came before us, whispering secrets about the cycle we're trapped in and the next universe waiting to be born. If extra dimensions exist, why can't we see or feel them? The answer might lie in their size, imagining dimensions curled up tighter than a coiled spring, so tiny that even atoms seem vast by comparison. Think of a garden hose stretched across a field. From far away, it looks like a simple line, a one-dimensional thread. But up close, you see its true nature, a tube with circumference, a hidden dimension wrapped tightly around itself. That's how some theories describe extra dimensions, as microscopic loops or folds woven into the fabric of space-time itself, too small for our eyes or instruments to detect. But gravity might be the exception, the one force that doesn't play by these rules. While electromagnetism and the other fundamental forces are trapped on our brain, bound to our three-dimensional world, gravity could be slipping through the cracks, leaking into higher dimensions like water seeping through a sieve. This would explain why gravity is so astonishingly weak compared to other forces. A fridge magnet can defy the entire planet's gravitational pull because most of that pull is bleeding away into dimensions we can't see, its strength diluted across realities beyond our own. Scientists are actively hunting for traces of these hidden dimensions, and the Large Hadron Collider is one of their most powerful tools. By smashing particles together at nearly the speed of light, researchers hope to create microscopic black holes, brief, flickering distortions in space-time that could reveal gravity's secret journey into higher dimensions. It's like tapping on a wall to listen for hollow spaces behind it. If the energy signatures or decay patterns of these collisions don't match our known physics, it could be evidence of dimensions lurking just beyond our perception. Another tantalizing clue could come from gravitational waves, ripples in space-time caused by cosmic cataclysms like colliding black holes. If extra dimensions exist, these waves might carry faint echoes of their structure, like sound waves changing as they pass through hidden chambers. Future observatories like the Laser Interferometer Space Antenna could detect anomalies in gravitational wave patterns, revealing whether space-time stretches into dimensions we've yet to map. The stakes couldn't be higher. Finding evidence of extra dimensions wouldn't just confirm Brane theory, it would rewrite the rules of reality, proving that our universe is more layered, more interconnected, and far stranger than we ever dreamed. And with every experiment, we're peeling back another corner of the cosmic curtain, inching closer to answers that could redefine existence itself. What if the mystery of dark matter, the invisible stuff that makes up most of the universe's mass, isn't about undiscovered particles at all, but about entire worlds hiding just beyond our reach? Here's the wild twist: dark matter could be ordinary matter, just like stars and planets, but trapped on a neighboring brane floating parallel to our own. We'd never see it because light can't jump between branes, but gravity could. That faint gravitational tug might be the only clue that an entire shadow universe is right beside us, its mass bending space-time in ways we can't explain. Think of it like living in a house with paper-thin walls. You can't see your neighbors, but when they blast music, you feel the bass vibrating through the floor. Dark matter could be the cosmic equivalent normal matter thumping away on a brane next door, its gravity rattling our universe like distant thunder. This would explain why dark matter doesn't interact with light or collide with ordinary matter the way particles in our universe do. It's not that it's made of some exotic substance, it's just locked in another layer of reality, forever out of sight but not out of reach. The beauty of this idea is how neatly it solves one of physics' biggest headaches. For decades, scientists have hunted for dark matter particles underground, in space, and inside giant colliders, but what if they've been looking in the wrong dimension? If dark matter is just matter on a nearby brane, we wouldn't need to invent new particles to account for it. The galaxies we see spinning too fast, the gravitational lensing we can't explain. All of it could be the fingerprints of a parallel universe brushing against ours, its gravity leaking through like light under a door. Even stranger, this could mean dark matter isn't evenly spread out. Just as planets and stars cluster in our universe, matter on a neighboring brane might clump in ways that create pockets of intense gravity, places where the invisible weight of another reality warps our cosmos. Some of the universe's most puzzling voids and filaments could be reflections of structures we'll never see, their presence revealed only by how they pull on us. And here's the kicker: if dark matter is brane-bound matter, then we might be someone else's dark matter too. On another brane, astronomers could be staring at their own sky, baffled by the same gravitational anomalies, never realizing with a ghostly mass tugging at their galaxies. It's a humbling thought that the universe's greatest mystery might not be a missing piece of our puzzle, but the shadow of another puzzle entirely, stacked right beside us in the cosmic dark. Quantum fluctuations, those tiny, unpredictable jumps in energy that constantly reshape the vacuum of space, might not stay confined to our universe. According to some interpretations of Brane theory, these quantum ripples could slosh between realities like water splashing between stacked bowls, leaving faint but measurable traces in our cosmos. One of the most tantalizing possibilities, the cosmic microwave background, the faint afterglow of the Big Bang, might carry imprints of these cross-dimensional whispers, subtle distortions that could be the first hard evidence of neighboring branes. Picture the quantum foam that physicists believe underlies spacetime, a seething, bubbling sea of virtual particles popping in and out of existence. Now imagine that foam isn't just beneath our feet, it's everywhere, permeating the higher dimensional space where branes float. When two branes drift close enough, quantum effects could tunnel between them, creating anomalies that defy conventional physics. It's like two soap bubbles nearly touching. Their surfaces quiver in response to each other's vibrations, even though they never truly collide. This isn't just theoretical sleight of hand. Researchers have scoured the cosmic microwave background for oddities, and some anomalies defy explanation. Certain regions of the sky show unexpected temperature fluctuations, cold spots, or asymmetrical patterns that don't fit the standard model of cosmology. Could these be the fingerprints of quantum interference from a nearby brane? The idea gains traction when you consider that if branes share a higher dimensional space, their quantum fields might subtly entangle, creating interference patterns visible in the oldest light in the universe. The implications are staggering. If true, we wouldn't just be detecting another universe, we'd be glimpsing the quantum heartbeat of a reality operating under entirely different laws. Imagine a brane where gravity is stronger or the speed of light is slower. Its quantum fluctuations might leave bizarre statistical signatures in our sky, like shadows cast from a dimension we can't otherwise perceive. Even more intriguing, this could explain the universe's puzzling uniformity. Inflation theory suggests the cosmos smoothed out in a fraction of a second, but quantum entanglement between branes offers an alternative. What if our universe's consistency isn't from rapid expansion, but from being echoed off a neighboring brane during its formation? Like two guitars placed close together, where plucking one string makes the other hum in sympathy, our universe's structure might have been tuned by quantum vibrations from another reality. The hunt for these anomalies is already underway. Next-generation telescopes and more precise measurements of the cosmic microwave background could reveal patterns that no single universe model can explain. If they find them, it wouldn't just confirm Brane theory, it would open a window into the quantum conversations happening all around us in dimensions just beyond our grasp. We might be living in a chorus of universes, each humming its own tune, yet forever bound by the faintest threads of quantum mechanics. What if the Big Bang wasn't an explosion in empty space, but a cosmic shockwave rippling through the surface of reality itself? Brane cosmology offers a radically different take on the birth of our universe, not as a fiery singularity, but as a distortion propagating through a higher dimensional membrane, like a drumhead vibrating after being struck. Picture this: instead of a lone spark in the void, imagine our universe as the aftermath of a colossal tremor, a ripple racing across the fabric of a brane. This idea flips traditional cosmology on its head. The standard Big Bang model describes an infinitely dense point suddenly expanding, but it doesn't explain what triggered that expansion or why the universe looks so remarkably smooth on large scales. Brane cosmology sidesteps these puzzles by proposing that the Big Bang was more like a dynamic event in a multidimensional landscape, a localized agitation that sent waves of energy surging through our brain, creating the matter, radiation, and structure we see today. Think of it like flicking a bedsheet. The initial jolt creates a traveling wrinkle, and everything we perceive, galaxies, stars, even time itself, is just the unfolding of that disturbance. The drumhead analogy is especially revealing. When you strike a drum, the skin doesn't just move in one place, it vibrates in complex patterns with waves spreading outward in all directions. Our universe might be the same, a standing wave frozen in the aftermath of that primeval strike, its harmonics encoded in the distribution of galaxies and the echoes of the cosmic microwave background. Even the universe's large-scale structure, those vast filaments of matter weaving through cosmic voids, could be the fingerprints of those early vibrations, patterns left behind as the brain settled into equilibrium. But here's where it gets truly fascinating. If the Big Bang was a brane event, it might not have been a one-time occurrence. Just as a drumhead can be struck repeatedly, branes could experience multiple collisions or disturbances, each spawning a new cycle of cosmic evolution. Some theories suggest our universe might even bear scars from earlier strikes, ancient imprints hidden in the fabric of space-time, like ghostly echoes of universes that came before. This perspective also solves one of cosmology's thorniest problems, the horizon problem. The universe's extreme uniformity, why temperatures are nearly identical in opposite directions, is hard to explain if distant regions never had time to interact. But if the Big Bang was a brane-wide event, like a simultaneous slap across an entire drumhead, uniformity becomes natural. The energy would distribute evenly from the start, eliminating the need for faster-than-light inflation to smooth things out. The implications ripple outward. If the Big Bang was a brane phenomenon, then the very laws of physics might not be fundamental constants but local byproducts of how our membrane vibrates. Change the frequency, and you'd get a different universe with alternate forces, particles, or even dimensions. It's a vision that turns cosmology into a kind of cosmic musicology, where the secrets of reality are written not in equations alone, but in the harmonics of higher dimensional vibrations. And if that's true, then the next great breakthrough in physics might not come from staring deeper into space, but from listening more carefully to the hum of the brain we call home. How do you test a theory that suggests entire universes might be lurking just beyond our perception? For Brane theory to move from dazzling speculation to solid science, we need real-world evidence, tangible clues that could confirm we're living in a cosmic stack of realities. Luckily, scientists aren't just waiting for answers to fall into their laps. They're actively hunting for footprints of higher dimensions and neighboring branes, using everything from colossal particle colliders to space-based gravitational wave detectors. One of the most dramatic experiments involves searching for microscopic black holes, tiny, fleeting distortions in spacetime that could reveal gravity's escape into extra dimensions. If branes exist, the Large Hadron Collider might be able to create these minuscule black holes by smashing particles together at nearly light speed. Normally, black holes require unimaginable densities to form, but in higher dimensional space, gravity could be stronger at tiny scales, making it easier to warp spacetime into these ephemeral knots. The catch: these black holes would vanish almost instantly, decaying into a shower of particles with telltale energy signatures. If detectors spot these unusual bursts, it could mean gravity is indeed leaking into dimensions we can't see, a smoking gun for Brane theory. But the search doesn't stop there. Gravity itself might hold other clues. Newton's laws, which describe how gravity weakens with distance, have been tested relentlessly for centuries. Yet at microscopic scales, smaller than a hair's width, some theories predict gravity could behave strangely if extra dimensions are in play. Experiments using exquisitely sensitive torsion balances or vibrating crystals are probing these tiny distances, searching for deviations that might betray the presence of hidden dimensions. Imagine blowing on a dandelion and noticing the seeds don't float away quite as expected. That subtle irregularity could hint at forces tugging from realities we can't see. Then there's the cosmic symphony of gravitational waves, ripples in spacetime from cataclysms like colliding black holes. Future observatories like the Laser Interferometer Space Antenna LISA could detect anomalies in these waves that point to higher dimensional effects. If spacetime is a membrane floating in a bulk dimension, gravitational waves might carry faint echoes of that structure, like sound waves bouncing through a labyrinth of unseen chambers. LISA ultra-precise measurements might catch these whispers, revealing whether gravity is truly spilling into dimensions beyond our own. Even the cosmos itself could be offering clues. The cosmic microwave background, the afterglow of the Big Bang, shows puzzling anomalies like cold spots or asymmetrical patterns that don't fit standard models. Some theorists suggest these could be bruises from ancient brane collisions or quantum interference from neighboring realities. Upcoming telescopes, like the European Space Agency's Euclid mission, will map these irregularities with unprecedented precision, searching for statistical fingerprints that align with Brane theory's predictions. The beauty of these experiments lies in their creativity. We might not be able to touch or see other branes, but by studying gravity's quirks, the birth cries of black holes, or the faint tremors in spacetime, we're building a toolkit to probe the very edges of reality. And if just one of these hunts pays off, it won't just confirm Brane theory, it'll rewrite our understanding of existence, proving we're part of something far grander than a solitary universe floating in the void. The holographic principle takes the mind-bending nature of Brane theory even further. What if the three-dimensional universe we perceive is nothing more than a shadow, a projection from information encoded on a two-dimensional surface at the edge of reality? This isn't just abstract philosophy, it's a radical idea born from black hole physics, where the amount of information a black hole can hold doesn't depend on its volume but on the surface area of its event horizon. Now combine that with Brane theory and suddenly our entire cosmos might be like a hologram, a three-dimensional movie playing out on a two-dimensional screen, with branes acting as the ultimate cosmic hard drives. Think of it like a credit card security chip. That tiny square holds all the information needed to represent your account, transactions, and identity, far more data than its physical size should allow. In the same way, the surface of a brane could encode the entirety of a universe within it, with every star, planet, and even your thoughts existing as patterns etched onto this fundamental layer. What we experience as depth, time, and space might just be the hologram's illusion, a trick of perspective where the real data lives on the brane's boundary. Black holes might be the key to unlocking this cosmic code. According to the holographic principle, a black hole doesn't destroy information when it swallows matter, it stores it pixel-like on its event horizon. Now imagine if black holes aren't just cosmic vacuum cleaners but portals between branes, their event horizons serving as transfer points where information is scrambled and sent into another reality. It's like burning a DVD. The data doesn't vanish, it's just rewritten in a form we can't easily read. This connection between branes and holography could solve one of physics' biggest puzzles: why the universe seems fine-tuned for complexity. If reality is fundamentally information-based, then the laws of physics might not be arbitrary rules but the operating system of a deeper computational structure. The brane isn't just a physical object, it's the substrate, the cosmic hard drive where the universe's code is written. And just as deleting a file on your computer doesn't erase it but marks the space as available, black holes might be the universe's way of recycling information into new forms across the brane stack. What's staggering is how this reshapes our understanding of existence. If the holographic principle is right, then the richness of our 3D world, every mountain, ocean, and galaxy, could be nothing more than a projection, a shimmering mirage painted onto the surface of a brane we'll never see. And if that's true, then the search for the theory of everything might not be about particles or forces at all, but about cracking the cosmic encryption written on the fabric of reality itself. The answers we're seeking could be hiding not in the stars, but in the invisible ink of higher dimensional data. Brane theory isn't just reshaping physics, it's infiltrating pop culture in ways that range from scientifically inspired to wildly imaginative. Take Hollywood's love affair with higher dimensions, for example. In Christopher Nolan's Interstellar, the portrayal of the Tesseract, a four-dimensional space where time becomes a physical dimension, borrows heavily from brane-inspired concepts. The film's protagonist navigates a labyrinth of bookshelves, glimpsing moments across time like pages in a cosmic flipbook. While the visuals are stunning, the science takes creative liberties. Real branes wouldn't manifest as a nostalgic library, but the idea of gravity transcending dimensions, that's straight out of string theory's playbook. Then there's Rick and Morty, where brane hopping is practically a weekend hobby. The show's infinite central finite curve plays with the idea of stacked realities, each with slight variations, some absurd, some terrifying. One episode even features a Brane Wars conflict where civilizations battle across dimensional membranes. It's a hilarious exaggeration, but buried in the chaos is a kernel of truth. If branes exist, their interactions could be chaotic, even violent. Of course, real brane collisions wouldn't involve talking pickles or sentient planets, but the show's writers clearly did their homework on multiverse theory before cranking the absurdity to 11. Literature isn't immune to brane fever either. Greg Egan's Diaspora explores civilizations living as digital constructs on higher dimensional branes, while Stephen Baxter's Raft imagines a universe where gravity is 1,000,000 times stronger, a nod to how brane-bound physics could warp fundamental forces. Even his Dark Materials dabbles in membrane-like worlds separated by subtle knife cuts. These stories often stretch the science, but they capture the essence of branes as frontiers, places where the rules change and anything might be possible. The trend isn't just about spectacle, it's a reflection of how brane theory taps into our deepest curiosities. We've always wondered what lies beyond the edges of our reality, and pop culture offers a playground to explore those questions without getting bogged down by equations. Sure, Hollywood trades precision for drama. No one wants to watch a 2-hour lecture on Calabi-Yau manifolds, but these portrayals keep the conversation alive. When Doctor Who weaponizes brain bombs or the OA uses dimensional travel as a metaphor for trauma, they're not just entertaining us, they're priming audiences to ask, could any of this be real? The best part, these creative takes might inspire the next generation of physicists. A teenager watching Interstellar might chase down Kip Thorne's papers, while a Rick and Morty fan could stumble into string theory wikis. Pop culture's role isn't to teach rigorous science, it's to spark wonder. And if a cartoon universe or a blockbuster collision gets someone hooked on the real mysteries of branes, then maybe those artistic liberties are worth it. After all, the line between science and fiction has always been a membrane. And who's to say which side we're on? If the cosmos is an infinite stack of realities, each brane a universe with its own stars, planets, and perhaps even versions of you, then everything we think we know about existence gets turned inside out. The sheer scale of this idea forces us to confront questions that blur the line between science and philosophy. If branes stretch endlessly through higher dimensions, does life emerge in all of them? Or is our universe a rare fluke, a cosmic oasis in a desert of lifeless membranes? And what does it mean for you if somewhere in another layer of reality, there's a doppelganger making choices you didn't, living a life you could have had? Consider the odds for a moment. In our universe, the constants of physics, the strength of gravity, the mass of an electron seem perfectly tuned for life. Tweak them slightly and stars wouldn't fuse atoms, molecules wouldn't bond, and life as we know it would be impossible. But if branes allow for infinite variations, then somewhere in the stack, there must be universes where those constants differ wildly. Some might be sterile voids, while others could harbor life stranger than we can imagine. The unsettling possibility, we might not be special at all, just one iteration in a boundless multiverse where life in some form is inevitable. This raises a haunting question about identity. If branes host parallel versions of Earth, then versions of you might exist too, alternate selves shaped by different choices, accidents, or even laws of physics. The person you are today could be one thread in a tapestry of possibilities, each life branching from moments as small as a missed bus or as large as a different evolutionary path. But here's the twist: even if those other yous share your genes and memories, they're not you. They're independent beings shaped by their own brain's history. The version reading this script right now is unique, anchored to this particular slice of reality. Yet the deepest implication might be existential. If branes are infinite, then every tragedy and triumph that's ever happened or could happen has played out somewhere in the stack. Wars unwon, loves unbroken, civilizations that never fell. It's a thought that's equal parts comforting and terrifying. No matter what choices you make, another reality holds the roads not taken. But instead of making our lives feel insignificant, this perspective could sharpen their value. If the brain stack is real, then this moment, this version of you, this universe, is the only one you'll ever experience. The others might as well be fiction. So where does that leave us? Maybe the answer isn't in searching for our place in the stack, but in embracing the mystery. Whether we're alone in the multiverse or one voice in a chorus of realities, the fact that we're here to ponder it at all is its own kind of miracle. The Brane multiverse doesn't diminish our existence, it expands the canvas, reminding us that the questions are just as thrilling as the answers, and who knows? Somewhere in the stack, another version of you is reaching the same conclusion. Time might not flow the way we think it does, at least not if branes have anything to say about it. Picture time not as a straight river, but as a thread woven through higher dimensional space, connecting moments like beads on a string that stretches across multiple realities. In this view, the past, present, and future could all exist simultaneously, stacked like pages in a cosmic book, with each brane representing a different moment or even a different timeline. And if that's true, then traversing time might not be about moving forward or backward. It could be about slipping between these membranes, hopping from one layer of reality to another. This is where wormholes come in. Kip Thorne, the physicist who inspired Interstellar's black hole visuals, proved that traversable wormholes, theoretical tunnels through space-time, could exist under the right conditions. These shortcuts through the universe rely on exotic matter with negative energy to keep them stable, threading the needle between collapse and rupture. But in the context of branes, wormholes might be even stranger, not just bridges across space, but conduits between universes and eras. Imagine punching a hole through the cosmic lasagna, connecting one slice of reality to another, where time runs at a different pace or even in a different direction. The implications are staggering. If branes overlap in higher dimensional space, a wormhole might not just link 2 points in our universe, it could tether ours to another membrane entirely, one where history unfolded differently or where the concept of now doesn't align with ours. Think of it like stitching together 2 pages from separate books. The words on each page were written independently, but the needle pulls them into the same moment. A traveler passing through might step into a world where dinosaurs never went extinct, or where humanity never evolved, all because they crossed into a brane where time's thread took a different path. But here's the catch: even if such wormholes exist, they'd likely be wildly unstable. A journey through one could stretch seconds into centuries or trap travelers in loops where cause and effect unravel. Thorne's calculations suggest that without precise control, wormholes would snap shut or explode from feedback loops like a microphone too close to a speaker, where the smallest vibration spirals into chaos. And if branes are involved, the risks multiply. A misstep could strand you in a reality where physics itself works differently, where atoms can't bond or light moves at a crawl. Yet the possibility remains tantalizing. Some theories suggest that quantum entanglement, the eerie link between particles across vast distances, might hint at hidden wormholes threading through higher dimensions. If entangled particles are like two ends of a wormhole stretched between branes, then the universe might already be riddled with these tiny, invisible tunnels waiting to be scaled up. Future civilizations could exploit them, not just to explore space, but to navigate the stack of realities itself. Of course, we're still light years from building or finding such a gateway. But the math doesn't forbid it, and if branes are real, then time travel might not be about rewriting history, but about discovering it, unfolding the layers of existence to see all the ways time's thread could have woven itself. The past, the future, and every alternate present might already be out there, pressed together in the cosmic dark, separated only by a dimension we've yet to learn how to cross. What if consciousness isn't confined to our brains but spills into the fabric of reality itself, echoing across the stack of universes like a note resonating through a cosmic instrument? This isn't just poetic speculation. It's a fringe but fascinating intersection of Brane theory and the mysteries of the mind. At the heart of it lies the hard problem of consciousness. Why does subjective experience exist at all? Why aren't we just biological robots processing data without inner light? Traditional science struggles to explain how mere matter generates feelings, colors, or the sense of self. But weave in Brane theory and suddenly the puzzle takes on a new dimension, literally. Some theorists propose that consciousness might not emerge from neurons alone, but could be a fundamental feature of the universe, like gravity or electromagnetism. This idea, called panpsychism, suggests that even particles have a rudimentary form of awareness. Now stretch that across branes. If consciousness is woven into the substrate of reality, could it ripple between membranes, connecting versions of you in parallel worlds? Imagine striking a tuning fork. The vibration doesn't stop at the fork. It travels through the air, through walls, even through your bones. If branes vibrate in higher dimensional space, could consciousness be a harmonic humming across realities? The implications are dizzying. Near-death experiences, déjà vu, or even creative inspiration might not be glitches in the brain but fleeting connections to other brains, moments when the veil between realities thins. Think of it like radio static. Most of the time you hear one station clearly, but sometimes interference bleeds through, hinting at other broadcasts just out of reach. If consciousness is a kind of signal, maybe it too can cross the static, blurring the lines between here and elsewhere. Then there's the wilder edge of this idea, shared dreaming. Cultures worldwide have myths of dream worlds where souls wander freely. Could these be subconscious glimpses of branes where the rules of time and identity unravel? In one universe, you might be asleep, in another, awake, yet somehow the boundaries blur. Even quantum mechanics toys with this notion. The observer effect suggests consciousness influences how particles behave, as if reality responds to attention. If branes exist, could this observer be entangled across membranes, subtly shaping multiple worlds at once? Of course, this is speculative territory, far from proven science. But the allure is undeniable. If consciousness transcends our brain, then death might not be an end but a transition, a shift to another layer in the stack. It's a thought that dances between physics and metaphysics, challenging us to ask, Are we solitary sparks or part of a vast, resonating symphony of awareness, echoing through dimensions we've yet to name? The answer, like consciousness itself, might be hiding in plain sight just beyond the edge of perception. If universes are stacked like pages in a cosmic book, then each page might tell a wildly different story, not just in its history but in its very laws. Picture a brane where light travels twice as fast, turning the night sky into a blinding tapestry of stars that flicker like strobe lights. Or another where gravity is 100 times stronger, crushing planets into dense marbles and pulling stars apart before they ever ignite. These aren't just thought experiments, they're plausible realities under Brane theory, where the tension of each membrane, the way it vibrates and stretches in higher dimensional space, could lock in its own unique physics like a fingerprint. The key lies in how branes interact with the bulk, the higher dimensional space they float in. Just as the tightness of a drumhead changes its pitch, the tension of a brane could determine the strength of its forces. Imagine plucking a guitar string. The tighter it's tuned, the higher the note. Now replace the string with a universe and the note with the speed of light or the strength of gravity. In one brane, tension might leave electromagnetism weak and gravity dominant. In another, it could flip the script, creating a reality where nuclear forces never bind atoms at all. The result, a multiverse where most branes are sterile wastelands, their laws too extreme for complexity to arise. This raises a chilling possibility. Our universe's finely tuned constants might not be special, just statistically inevitable in an infinite stack. For every brane like ours, where carbon can form and stars burn steadily, there could be 1 trillion others where physics scribbles only chaos. Some might have time that flows backward, or dimensions that unravel matter like loose thread. Others could harbor forces we've never imagined, weaving matter into shapes beyond our comprehension. The eerie fine-tuning we observe, the exact balance that lets galaxies and life exist, might simply be survivorship bias. We're here to wonder about it because, well, we couldn't exist anywhere else. Yet even in this sea of hostile physics, life might find stranger paths. A brane with hypercharged weak forces could birth civilizations powered by nuclear decay instead of sunlight. One with slower light might see creatures processing thoughts at glacial speeds, perceiving microseconds as hours. The true marvel isn't that our branes' rules allow life. It's that any combination could. The math suggests that even in the most exotic branes, complexity might emerge in ways we'd never recognize. Dark matter could be someone else's stars. A collapsing dimension might be another's breathable sky. The takeaway, Brane theory doesn't just expand our map of reality, it explodes it. Suddenly, the search for extraterrestrial life isn't limited to planets in our cosmos. It stretches across the stack, hunting for echoes of awareness in universes where physics itself is alien. And if we ever crack the code of brane tension, we might not just understand our place in the multiverse. We could learn to read the signatures of other membranes, listening for the hum of realities where the drumhead vibrates to a different beat. Picture this: a silent, invisible force is pulling our universe toward another reality. Not in millions of years, but now, as you watch this, somewhere in the higher dimensional darkness, another brane drifts closer, its gravity warping the fabric of our cosmos like a shadow stretching across a wall. When not if these membranes collide, the result won't be a distant cosmic fender bender. It could be an apocalypse or a resurrection. Brane collisions aren't gentle. Imagine 2 sheets of sandpaper scraping together at light speed. The energy released would dwarf the Big Bang, shredding spacetime itself. Galaxies would unravel like threads in a tornado, atoms torn apart by forces we can't yet name. But here's the twist: this annihilation might not be the end. Just as the last collision birthed our universe, the next could reboot reality entirely, a cosmic control alt-delete where physics gets rewritten from scratch. Stars might reignite under new laws, matter reforge into unfamiliar shapes, and time itself start counting from zero. Contrast this with the universe's other possible endings. The heat death where entropy wins, stars burn out, and space becomes a frozen graveyard of drifting particles, feels like a slow sigh into nothingness. The Big Rip where dark energy shreds even atoms is a violent but lonely demise. Both are terminal but brane collisions, their cosmic punctuation, not a period. Death isn't the finale, it's the prelude to another verse in an endless song. The evidence might already be written in the sky, those strange cold spots in the cosmic microwave background. They could be bruises from past collisions, scars from when our universe last hit reset. And if the cycle holds, the next reboot might be closer than we think. Some models suggest dark energy's acceleration, the force pushing our universe apart, is actually the tug of an approaching brane, reeling us in for another cosmic collision. This cyclical dance flips how we view existence. Most apocalypses are final, but in a brane multiverse, destruction is just metamorphosis. A burned forest feeds new growth. A supernova seeds planets, and a colliding brane. It might be the universe's way of breathing in again after the long exhale of expansion. The terrifying part isn't that everything ends, it's that everything begins again, unrecognizable without us. Yet there's strange comfort in that. If branes collide in endless cycles, then every possible reality, every version of you, every permutation of history will eventually flash into being, burn bright, and dissolve back into the bulk. The details change, but the song remains. You're here for this verse. The next universe's inhabitants will never know ours existed, just as we may never know what came before. The cycle doesn't care about memory. It only knows rebirth. Not every physicist is ready to embrace Brane theory as the next great paradigm shift. For skeptics like Neil Turok, former director of the Perimeter Institute for Theoretical Physics, the idea of floating membranes in higher dimensions isn't just speculative, it risks crossing the line into untestable metaphysics. His critique cuts to the heart of modern physics. If a theory doesn't make predictions we can observe or measure, is it still science or just elegant mathematical storytelling? Turok champions alternatives like the cyclic universe model, where the Big Bang isn't a brane collision but a bounce, a universe contracting and rebounding without extra dimensions. To him, adding unseen branes is like inventing invisible dragons to explain scorch marks. It might fit the facts, but it's not falsifiable. This debate isn't just academic. The scientific method thrives on testability. Einstein's general relativity predicted light bending around the sun, a claim verified during a 1919 eclipse. But branes, so far, no experiment has directly detected them, and critics argue we're building castles in the air. Imagine accusing someone of stealing your keys when they might not even exist. That's the frustration some feel with brane theory. It's dazzling math with no smoking gun. Even the search for higher dimensions relies on indirect hints, tiny deviations in gravity or exotic particle decays that could have mundane explanations. Yet defenders counter that all groundbreaking theories faced skepticism before evidence arrived. Black holes were once deemed mathematical quirks, now we photograph them. The Higgs boson took 50 years to confirm. Brane theorists argue we're in the early stages, not a dead end. They point to anomalies like the cosmological constant problem, why vacuum energy is absurdly weaker than predicted as potential brane fingerprints. If gravity leaks into extra dimensions, it could explain the discrepancy without inventing new particles. The line between visionary and unverifiable is razor thin. String theory, brane theory's parent, has been mocked as not even wrong, too flexible to disprove. But science often progresses through bold speculation refined by data. Dark matter was once dismissed as ad hoc, now it's textbook astrophysics. The real test for branes may come from next-generation gravitational wave detectors or quantum gravity experiments, where subtle space-time tremors could reveal hidden dimensions. Until then, the debate rages. Are we glimpsing reality's deepest layers or chasing shadows in the math? What makes this tension fascinating is how it mirrors physics' identity crisis. Is our job to describe nature as simply as possible, or to explore every beautiful possibility, even if it stretches credulity? Turok's cyclic universe is elegant in its minimalism. No extra dimensions, just gravity and quantum mechanics looping eternity. But Brane advocates sea beauty in complexity, a multiverse where every mathematical structure gets its own reality. Both camps agree on one thing: the universe is stranger than we imagine. The disagreement is whether it's stranger than we can imagine. That's the thrilling edge where science dances with philosophy and where the next revolution might be waiting. At the heart of Brane theory lies a world of breathtaking mathematical beauty where abstract shapes fold and twist through hidden dimensions like cosmic origami. Take Calabi-Yau manifolds, for instance. These intricate six-dimensional shapes are the hidden scaffolding of string theory, curled up so tightly that they're invisible to us, yet they shape the very fabric of reality. Picture a crumpled piece of paper. From a distance it looks flat, but up close its complex folds create pockets and ridges we never knew were there. That's how Calabi-Yau manifolds work. They're the hidden geometry that determines how strings vibrate, which in turn defines the particles and forces in our universe. Every electron, every photon, every quark might owe its existence to the way these invisible structures curve and intersect in higher dimensional space. Then there are D-Brane's dynamic surfaces where strings can anchor themselves like musical notes pinned to a vibrating string. These aren't just abstract concepts, they're the reason we can imagine our universe as a membrane floating in a higher dimensional bulk. D-branes come in all dimensions. A zero-dimensional D-brane is a point, a one-dimensional one is a line, and so on, up to the three-dimensional brane we might call home. What's mesmerizing is how they interact. When two D-branes collide, strings stretching between them can create new particles, almost like sparks flying when stones are struck together. This isn't just math, it's a recipe for reality where the clash of membranes could birth everything from quarks to quasars. And then there's M-theory, the grand unifier lurking behind the curtain. If string theory is the symphony, M-theory is the conductor, revealing how all the pieces fit together. It suggests that the five competing versions of string theory aren't rivals at all. They're different perspectives of a single, deeper truth, glimpsed through the lens of an 11-dimensional universe. Imagine looking at a hologram. Tilt it one way and you see a bird, tilt it another and it's a tree. M-theory does the same for branes and strings, showing how they're all facets of something greater. It's here that the math reaches its most elegant, suggesting that our universe's complexity arises from the vibrations of tiny, higher-dimensional membranes dancing through space-time. The sheer artistry of these equations is what makes physicists fall in love with the idea. There's a rhythm to the math, a symmetry so perfect it feels like uncovering the universe's blueprints. When you sketch a Calabi-Yau manifold or trace the interactions of D-branes, you're not just doing abstract calculus, you're mapping the hidden architecture of existence. And if the equations are right, then every star, every atom, and every thought might just be notes in a cosmic symphony, played on the strings of a higher dimensional world we're only beginning to hear. Across cultures and centuries, humans have woven stories of layered realities, cosmic tiers where gods, spirits, and alternate versions of existence interlace with our own. Hinduism describes lokas, 14 planes of reality stacked like petals of a lotus, from the earth-bound Bhuloka to the divine Satyaloka. Jewish mysticism speaks of the Sephirot, the 10 emanations of the tree of life bridging the infinite and the material. Even indigenous Australian Dreamtime speaks of a shadow world mirroring our own. Strikingly, these aren't just metaphors, they're uncanny echoes of Brane Theory's vision of a multiverse, suggesting that science and spirituality might be circling the same truth from different directions. Take the Hindu concept of Brahma's golden egg, the Hiranyagarbha, from which all universes hatch. Ancient texts describe it as a shell containing countless nested layers, each with its own laws and beings. Swap egg for brain, and the resemblance is startling. The Puranas even speak of cyclical universes being born and destroyed, an eerie parallel to the Ekpyrotic model's colliding membranes. Similarly, Kabbalah's Ein Sof, the infinite, dimensionless divine, radiates through the Sephirot like gravity leaking between branes, structuring reality through hidden dimensions. Could these traditions have intuited a cosmic architecture that science is only now mapping with equations? The overlaps grow stranger when you examine creation myths. The Norse Ginnungagap, a primordial void between fire and ice realms, mirrors the higher dimensional bulk separating branes. The Maya believed in 13 heavens and 9 underworlds, layered realms accessed through sacred portals, not unlike theoretical wormholes between membranes. Even the Christian concept of heaven as a dimension beyond earthly perception aligns with the idea of branes as parallel planes, invisible yet coexisting. These aren't mere coincidences, they're recurring intuitions about reality's layered nature, encoded in symbols long before telescopes or particle colliders. Yet the tension between these frameworks is undeniable. Science demands testable evidence while spirituality embraces mystery. Branes are mathematical constructs, lokas are realms of divine play. But what if both are grappling with the same elephant in the cosmic dark? The physicist's higher dimensional bulk and the mystic's subtle plane could be linguistic cousins, one quantified, the other poetic. After all, dark matter was once the stuff of myth until science gave it a name. Perhaps the most profound intersection lies in consciousness. Both Brane theory and esoteric traditions suggest that awareness might transcend our local reality. Hindu sages speak of turiya, a state of consciousness beyond waking, dreaming, and deep sleep, a fourth layer echoing the idea of higher dimensional perception. If branes vibrate in dimensions we can't see, could meditation or mystical experience offer fleeting glimpses across the stack? Science dismisses this as untestable, but the persistence of these experiences across cultures raises tantalizing questions. The divide isn't insurmountable. Just as Newton's laws gave way to Einstein's relativity, our understanding of reality keeps expanding. Brane theory doesn't validate any single theology, but it opens a dialogue, a space where ancient awe and modern rigor might meet. Whether you see the cosmic stack as equations or emanations, one truth remains: the universe is vaster, weirder, and more connected than we ever dreamed. And that's a revelation both lab and temple can celebrate. Ever tried explaining the third dimension to a stick figure living in a flat, two-dimensional world? That's the predicament we face when imagining branes' realities stacked in dimensions we can't see or touch. But here's a trick: borrow from the classic Flatlander thought experiment. Picture a universe as thin as a sheet of paper, where beings like squares and triangles live their entire lives unaware of up or down. To them, a three-dimensional apple passing through their plane would appear as a dot that grows into a circle, then shrinks back to nothing. Their confusion mirrors ours when grappling with higher dimensions. Now flip the script. What if we're the Flatlanders, oblivious to the up that lies beyond our brain? Every unexplained gravitational tug or cosmic anomaly could be the higher dimensional equivalent of that apple, hints of a reality brushing against ours. Take another analogy: ants on a floating leaf. They scurry across its surface, never suspecting the vast pond beneath. To them, ripples from a fish jumping near by might seem like magic, random vibrations with no visible cause. That's how gravity could behave in a brane multiverse, a force leaking from a hidden dimension, its source forever out of view. Try this at home. place a marble on a stretched bedsheet and watch it dip the fabric. The indentation is like a brain warped by gravity, with the marble representing a universe next door. Now imagine another marble rolling nearby, its path subtly altered by the first one's dent. That's the dance of brains, unseen but bending each other's fate. Here's where it gets interactive. Close your eyes and picture standing in a pitch-black room, arms outstretched. You know there are walls, but you can't see them, just like we can't perceive adjacent brains. Now imagine another version of you in that darkness, inches away, reaching back. That's the eerie intimacy of parallel realities in Brane theory. You'll never touch, but your shadows might overlap. Some theorists even suggest déjà vu could be fleeting moments when brains vibrate in sync, letting fragments of another timeline bleed through. To really feel the concept, try this mental exercise. Stack books on a table, each representing a brain. Slide a playing card between two pages. That's you, a 3D being, intersecting a 2D plane. The card's edge casts a shadow the book's flat inhabitants might detect as a mysterious line. Now extrapolate. Could our entire universe be the shadow of a higher dimensional object passing through? The idea isn't just poetic, it's rooted in serious physics, like the holographic principle, where our 3D reality might be a projection from a 2D boundary. The real power of these thought experiments isn't just in understanding brains. It's in rewiring how we perceive reality itself. Every time you notice a reflection in a window, consider this: the world beyond the glass isn't vanishing when you look away. It's still there, separate but parallel. Brains could be like that, realities hovering just beyond the mirror of our perception, waiting for science to shine the right light. Imagine a spacecraft not bound by the limits of our universe, a probe designed to slip between brains like a fish leaping between ponds. This isn't just fantasy, it's the tantalizing promise of brain-inspired engineering. Picture a vehicle sheathed in exotic matter, its hull tuned to resonate with higher dimensional vibrations, allowing it to peel away from our brain like a sticker lifting from glass. Theoretically, such a craft could exploit quantum tunneling effects at macroscopic scales, borrowing energy from the vacuum to punch through the membrane barrier. The catch: even if we cracked the physics, the energy requirements would dwarf anything our civilization can produce. We're talking about harnessing the power of colliding neutron stars just to open a microscopic rift. And then there's the navigation problem. Without a map of the bulk, the higher dimensional space between brains, a brain-hopping probe might vanish forever, lost in dimensions where our laws of physics don't apply. Now consider gravity shields, devices that manipulate the leakage of gravity between brains to create protective bubbles around spacecraft or cities. If gravity is the only force seeping through dimensions, then controlling its flow could revolutionize everything from space travel to architecture. Picture a lunar colony encased in a gravity-diffusing field, neutralizing deadly cosmic rays by bending their trajectories into higher dimensions. The math suggests such shields might be possible using materials with negative energy densities, like metastable dark energy condensates. But the ethical quagmire is profound. Tinkering with gravity at this scale could destabilize planetary orbits or accidentally puncture spacetime, creating artificial singularities. One miscalculation might unravel the local brain like a snagged thread in cosmic fabric. Then there's the most mind-bending possibility: dimension-unfolding computers. Traditional chips process information in 3 dimensions, but what if we harnessed higher dimensional geometries for computation? Imagine processors built from folded D-branes, where qubits exist simultaneously in multiple dimensions, solving problems intractable to classical machines. A single calculation could unfold across brains, with each dimension adding exponential processing power. The prototype might resemble a quantum computer cooled near absolute zero, its qubits replaced by vibrating strings anchored across compactified Calabi-Yau manifolds. The catch, such a device wouldn't just compute, it might inadvertently rewrite local spacetime. Every operation could leave micro-tears in the brain, accumulating into dangerous topological defects. And who gets to wield this godlike power? The first nation or corporation controlling dimension unfolding tech could crack encryption, simulate alternate histories, or even engineer new physical laws within confined spaces. The ethical dilemmas pile up like stacked realities themselves. Should we probe branes if we risk colliding with inhabited universes? Does humanity have the wisdom to manipulate cosmic architecture without becoming the bull in the multiverse's china shop? Ancient myths warned of Pandora's box, but no legend prepared us for the temptation of playing with the very scaffolding of existence. Perhaps the ultimate test of brain tech won't be engineering, but restraint, the humility to leave certain doors between worlds forever locked. The next decade could rewrite physics as we know it, not with telescopes or chalkboards, but with quantum simulations so precise they'll let us watch brains collide in digital slow motion. Imagine a supercomputer so powerful it can model the birth of universes, simulating how membranes ripple, warp, and rebound in higher dimensional space. Teams at MIT and CERN are already partnering to build quantum algorithms that mimic brain dynamics, treating each qubit as a fragment of a cosmic membrane. These aren't just abstract exercises, they're dress rehearsals for reality. By tweaking parameters, adjusting brain tension, bulk dimensionality, or collision angles, researchers might finally answer why our universe has exactly 3 spatial dimensions, or why dark energy's strength is so eerily fine-tuned. The simulations could even reveal signatures of past brain collisions, hidden in patterns we've missed until now. Meanwhile, artificial intelligence is becoming the unsung hero of string theory's most vexing equations. For decades, physicists wrestled with landscape problems, the dizzying 10 to the 500 possible configurations of string theory's extra dimensions. Enter neural networks trained on millennia of mathematical literature, now spotting shortcuts humans overlooked. Google DeepMind's AI recently discovered new geometric shapes in Calabi-Yau manifolds, structures critical for compactifying hidden dimensions. These breakthroughs aren't just academic, they're narrowing the search for which brain configurations could realistically spawn a universe like ours. AI might soon pinpoint the precise mathematical fingerprint of our brain's higher dimensional shape, turning abstract theory into testable prediction. But the real game-changer lurks underground. Next-generation particle colliders like the Future Circular Collider, slated to eclipse the LHC's power by 2040. With beams colliding at energies approaching 100 tera-electronvolts, scientists could create conditions last seen microseconds after the Big Bang, potentially sparking micro-black holes or detecting gravity's leakage into extra dimensions. One tantalizing proposal involves firing particle beams parallel to suspected brain orientations, hunting for anomalous energy losses that hint at higher dimensional escape routes. It's like listening for echoes in a canyon. If particles vanish just slightly faster than physics allows, they might be slipping into the bulk. What ties these threads together? A growing consensus that cosmology's next revolution won't come from staring deeper into space, but from engineering tools sensitive enough to probe the edges of our brain. Some theorists predict we're less than a decade from detecting gravitational anomalies that betray a neighboring universe's pull, or finding quantum entanglement patterns that only make sense if particles are whispering across membranes. The implications would dwarf the Copernican or quantum revolutions, proving we're not just one universe among many, but one layer in an infinite cosmic stack. The race isn't just to understand brains, it's to touch the fabric of reality itself. Ever wonder what your personal multiverse would look like if you could sketch it on a napkin? Now's your chance to play cosmic architect. Grab a pen, a scrap of paper, or just picture it in your mind. Would your brain stack neatly like pancakes, each layer a slightly altered version of reality? Or maybe they'd twist into a Möbius strip of tangled timelines where past and future loop back on themselves. You could even go full sci-fi and add a mirror universe where everyone has goatees, or a brane where gravity works sideways and cities cling to skyscraper walls like geometric ivy. The beauty of brane theory is how it turns abstract physics into a playground for the imagination. Think about the tropes you'd include. A reality where dinosaurs never went extinct and humans evolved alongside raptor engineers. A brane where the laws of thermodynamics run backward, turning spilled coffee into pristine cups and old age into youth. Maybe even a universe where sound and light swap properties, turning concerts into blinding light shows and sunsets into symphonies. This isn't just whimsy, it's a thought experiment that reveals how deeply brane theory reshapes our sense of possibility. Every what-if scenario becomes a legitimate question when universes are just membranes away. Now, here's the fun part. Share your sketch or describe it in the comments. Tag the video with #MapYourBrane and let's build a crowdsourced multiverse. Whoever dreams up the wildest brane, whether it's a reality made of sentient math or a universe where time flows in spirals, gets unofficial bragging rights as chief architect of the cosmic stack. Bonus points if you sneak in a nod to classic sci-fi, like a Star Trek-style mirrorverse or a dark city where the sky rewrites itself at midnight. The real magic here. This isn't just creative storytelling. Every doodle, every what-if scenario is a tiny window into the same questions physicists wrestle with. When you imagine your brane's rules, you're tapping into the same curiosity that drives string theorists to sketch Calabi-Yau manifolds or cosmologists to model colliding membranes. So go ahead, draw the multiverse you'd want to explore. Who knows, the future might just prove you right. From colliding universes birthing new realities in cosmic fireworks to gravity slipping between dimensions like whispers through a wall, brane theory stretches the limits of what we thought possible. Picture it, an infinite stack of universes, each a shimmering membrane vibrating with its own laws, its own history, its own version of you. Somewhere in that cosmic lasagna, dark matter could be the weight of a neighbor's stars pressing against our brane, while quantum ripples from other realities leave ghostly fingerprints in our oldest light. The wildest ideas, like time as threads woven through higher dimensions or consciousness resonating across branes, aren't just sci-fi dreams. They're frontiers where physics and philosophy collide, challenging us to rethink existence itself. Here's the kicker: you might be living this moment in multiple branes right now. One where you clicked this video, another where you didn't, and a third where gravity is sideways and your coffee floats off the table. That's the thrill of brane theory. It turns what if into why not, inviting us to question everything. So stay curious. The next cosmic revelation could be hiding in the math, the next experiment, or even the sketch you doodled tonight. If you're hungry for more mind-bending science, hit like, subscribe, and let's keep unraveling reality's deepest layers one brane at a time.